Okay, good day, boys and girls. This is AP Calculus Summary Review. I am Mr. McCulley. This is SR number 6, Asymptotes and Partial Fraction Decomposition. I don't want to waste your time, so let's get right to it. Today we're going to talk about vertical and horizontal asymptotes of a rational function, and then we are going to find the partial decomposition of a rational function. First one we did in Algebra 2, also in pre-calculus. The second one we did in Algebra 2 very quickly, so we're going to spend a little bit more time on that one. The first one we'll go through fairly quickly. So a vertical asymptote is an imaginary boundary line which correspond to the non-reducible zeros of the denominator of a rational function. And we're talking about rational functions in vertical asymptotes, so there are other instances in which you could have a vertical asymptote other than a rational function like we have up here. So what do I mean versus a reducible and versus a non-reducible zero in the denominator? Well, let's look at this particular function right here, and it's f of x equals x squared plus 4x plus 4 over x squared plus 5x plus 6. Now, both of these are quadratics and both of these are factorable, and if I factor them, I get on the top here, it would come out to x plus 2 and x plus 2. On the bottom, I would get x plus 2, and I would also get x plus 3, and that would give me, make that a plus, and that would give me the x squared plus 5x plus 6. Now, if you look at this thing right here, there are two values for x that would give me divisions by 0. If I plugged in -2 here, I would get a 0, and 0 times whatever this would be 0, and I'd have a division by 0. So -2 is going to be a discontinuity, a value that's going to cause a hole in my graph. But also, if I plugged in -3 here, I would get another discontinuity. Now, the difference between a reducible and a non-reducible zero is if there is a factor in the numerator that cancels out. If you notice, I could factor out one of these two x plus 2's and cancel those out. Now, does that mean that this is gone? No, I'm still going to have a hole here at -2, but the graph is going to look as if it was x plus 2 over x plus 3. Now we can look at that thing. Now if you look at what I have here, you'll see I have my x squared plus 4x plus 4 all over x squared plus 5x plus 6. Now when I graph this thing, you'll notice I only have one horizontal or one vertical asymptote here, and this is going to be at -3. There is no vertical asymptote at -2, and it doesn't look like there's a hole there, and that has to do with the way things are graphed. But if you look at our table here, at both -3 and at -2, we've got an error. We've got that division by 0 error. So even though we don't have a vertical asymptote at both places, we have one where we have the irreducible. I can't reduce this -3 asymptote. All right, so let's talk about horizontal asymptotes. Horizontal asymptotes generally describe what the function does as the magnitude of x gets larger, both positively and negatively. So just some notes to think about what that really means. Near the origin, the function can cross the horizontal asymptote. So we could cross it lots of times, as much as we get close to the origin. What we're talking about is what the function does towards the extremely positive and the extremely negative functions. Rational functions do not necessarily have horizontal asymptotes. Sometimes you could have slant asymptotes. Sometimes you have no asymptote at all for horizontal. Horizontal asymptotes can exist in contexts other than rational functions. This isn't the only way that you could get a horizontal asymptote, but it's one that we're going to see quite a bit in AP Calculus. And then how do we figure out what the horizontal asymptote is? Well, it's dependent upon the ratio of the degree of the numerator and denominator. So what we're going to do is we're going to look at the highest powered term of both the numerator and the denominator, and we're going to compare them according to these following rules. So when we look at this thing right here, so when I'm asked to find my horizontal asymptote, I'm going to compare the degrees. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is a ratio of the leading coefficients. And if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is 0. So let's look at a couple of examples here. All right, so if I look at this particular function right here, and it says find the horizontal and vertical asymptotes of this thing. If I want to look at my vertical ones first, that'll probably be easier. I want to factor these two things. So the top one we've already seen, it's x plus 2 and x plus 2. And then the bottom, let's see here, I'm going to have 2x and 2 times 3 is 6 plus 1. So we're going to go plus 1 and then x plus 3. I think that'll work. 2x times 3 is 6x. 1 times x is 1x. That'll give me my 7. 1 times 3 and then 2 times x. So I have that. So now when I look at this function right here, I notice that none of these things cancel out. None of the factors cancel with another factor. So in both instances, the value for x that makes this 0 and the value for x that makes this factor equal to 0 are both going to cause me to have vertical asymptotes. So for this one, my vertical asymptotes are going to be at x. Well, we'll do the easy one first. Negative 3 makes that one. Now, if you can't see this, that's going to be negative half. We want to know what makes that equal to 0. So you could just go 2x plus 1 equals 0. Subtract 1, 2x equals negative 1, and then x equals negative 1/2. That's going to be my other vertical asymptote. So I'm going to have my negative 1/2 as my second asymptote. Now, if I want to find my horizontal asymptote, now I need to compare the degrees. So the degree of the numerator is 2, and the degree of the denominator is also 2. So if I go back to my little cheat sheet here, the degree of the numerator, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of the leading coefficients. So my leading coefficients are going to be 1 and 2. So my horizontal asymptote is going to be 1/2. Now we can look at that fairly easily. If I go to my y equals up here, that one stays the same. All I got to do is add my, let's go over here, maybe, or it's going to lock up on me. Well, that stinks. It just locked up on me. Let's see, we'll cancel this. Sorry about that, folks. If I have time, I'll edit it out. All right, let's bring that back up. Close that. Y equals. All right, so let's see here. It was x squared plus 4x plus 4, not 7, divided by, let's see here, I had 2x squared plus 7x plus 3 on the bottom. And if we hit graph, you can see that we have, again, a vertical asymptote at 3, and then another vertical asymptote at negative 1/2, negative 3, negative 1/2, and then our horizontal asymptote is again going to be at just 1/2. So not too bad. All right, let's look at this thing. Let's look at this next one. So I look at this one, and again, I'm going to try and factor. And this one on the top, I'm going to get 2x, and then we'll go, it's going to be, I think we're going to do minus 1 here. 2x minus 1, and then x plus 3. 2x times 3 gives me 6x, and then negative 1 times x gives me negative 1. That gives me my negative 5. And then the bottom does not factor. So again, I am in an instance where nothing cancels here. Neither of these two factors cancel. So I have only one vertical asymptote, and that's at x equals 0. Why? Because 0 is the only thing that makes that equal to 0. Then, if I want to do the horizontal asymptote, I look at the degrees of the numerator and the denominator. And so this degree is 2, this degree is 1. So since the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So I can just go right back to here and say none. And we can look at that real quick. Hopefully it won't crash on me. So let's see here, parenthesis 2x squared, that was a plus 5x minus 3, parenthesis, was that right? Yep. And then divided by x. And if you look at that, you'll see that I have no horizontal asymptote, but I still have my vertical asymptote at 0. All right. Okay, moving on. Now, the hard part. Partial fraction decomposition. I'm going to kind of go one direction and then go backwards to try and explain this. But consider the fact or the act of adding two simple rational equations. And when I say we're going to add two simple rational equations, I'm talking about this expression right here. This 2 over x plus 3 over x plus 1. Now, if we wanted to do that, and just like any other adding of fractions, you would have to find a common denominator. And the least common multiple of x and x plus 1 would be x times x plus 1. So when I take this original expression right here, and I guess I'm just going to kind of highlight as I go along. When I take this original expression here, my least common multiple for x and x plus 1 is going to be x times x plus 1. So this first fraction here, I'm going to multiply this first fraction here by a funky 1. It's x plus 1 over x plus 1. I'm going to multiply the second fraction by x over x. Now what that does is that makes the denominator in both instances x plus 1 times x. Then I'm going to distribute here. So 2 times x is 2x, 2 times 1 is 2, and then x times 3 is 3x. So I'm adding my fractions here. So I want to collect my like terms, and I have 5x plus 2, and then x squared plus x. So I'm just simplifying here. So x times x is x squared, and x times 1 is x. 2x plus 3x give me 5x, and the 2 has nothing to combine with. Now, that's adding fractions. That's not what we're trying to get to, but what we're trying to get to is this partial fraction decomposition, which is going to ask us to take this added function and break it down so that it is the sum of some other fractions, specifically linear linear denominators as far as what's going on. So how am I going to do that? Well, let's say we take this original function again, and the first thing that I'm going to want to do here is I'm going to want to factor the denominator. And so when I see something that looks like this, the first thing I want to do is I want to factor the denominator into linear fractions if possible, or linear factors if possible. Now there is one little asterisk that goes with that, and I'll do an example of that later, but you want to try, for the most part, to try and get them into linear factors if that is possible. All right, so we're going to set the original fraction equal to a sum of the fractions. Oh, and then this should be 1, not on, sorry. I didn't catch that typo. 1 for each factor in the denominator with a different variable for each of those fractions. So I'm going to have one fraction with x as a denominator and one fraction with x plus 1 as a denominator. And you can see that I have this entire expression. So you'll see that I have my original fraction, and then I'm going to have two fractions that I'm trying to figure out one with each of those linear factors as the denominator. So let's see, do I go and do that on the next page? Yes, I do. All right, so here's what I'm going to do. I'm going to multiply both sides by the x times x plus 1, or you could say it's x squared plus x. The problem with that is that you're not going to get things to cancel out. So here's what happens. X times x plus 1 is x squared plus x. So when I multiply this first fraction here by this expression, these two things cancel. You get x squared plus x and x squared plus 1 to cancel. And what happens when that happens is you're just left with 5x plus 2. Now, when you multiply x times x plus 1 times a over x, the x's cancel, and then you have x plus 1 times a, which would be a times x plus 1. All right. Now, oops, didn't want to go that far. Now, when I multiply x times x plus 1 times b over x plus 1, the x plus 1 and the x plus 1 cancel. Oops, didn't want that. The x plus 1 cancel, and I'm left with x times b, which would be bx. All right, so I'm going to simplify a little bit. I'm going to distribute my a, so I have a times x and then a times 1, which give me ax plus a. Simplify, and then here's what I'm going to do. Notice I'm going to try and collect my like terms here. So I've got ax and bx, and I have just a constant a. So if I factor out an x from both of these terms, I'm left with a plus b times the quantity x, and then I have the constant a. So I'm going to match the linear term and a constant and then solve as a system of linear equations. So what I'm saying here is that this 5 coefficient, because it's of the x, has to be equal to a plus b. So 5 has to equal a plus b because the x coefficient on the right-hand side has to equal the x coefficient on the left-hand side. Now the good news is I don't have an expression over here. I've got an a, that's my constant, and 2 is my constant. So this system of linear equations is pretty easy. I know that a has to equal 2. And I know that when I go a plus b, I have to get 5. That means that obviously if a is 2, 2 plus b equals 5, well then b has to equal 3. All right, did I finish here? All right, so I'm solving, so I guess I had another page there. So again, a plus b has to equal 5 and a has to equal 2. So if I plug in, oh, I think I plugged in the wrong place. So let's just scratch this out. We won't even pay attention to this. I'll change it for later. At any rate, this expression here has to be 2 plus b equals 5, and then b will equal 3. And since a equals 2 and b equals 3, the partial fraction decomposition is going to be this expression. And notice right here, this is what we got when we started way back here. We started with this original stuff, we added it together, and then we decomposed it. All right, so what about repeated linear factors? What happens if you've got a bunch of repeated linear factors? Well, before I get into it, let's look at a simpler problem and see what might happen here. So let's say I added 1/3 plus 1/9 plus 1/27. Now notice this thing here is 3. This denominator is 3. This denominator is 3 squared, and this denominator is 3 to the third. Well, what is the least common denominator for all three of these values? The least common multiple for all three values is going to be 27. So for me to get the same value for each, I'm going to have to take this 1/3, and I'm going to have to multiply it by 3 squared over 3 squared so that I get 27. The 1/9 I have to multiply by 3 over 3 so that I get 27th. And the 27th, it doesn't change, so I'm going to leave that there. So now I get 9 over 27 plus 3 over 27 plus 1 over 27 is going to equal, let's see here, 9 and 3 is 12, and 1 is 13/27. And since 13 is a prime number, we're done there. So let's look at it in the context of this. What am I going to do if I have a repeated linear factors? Well, I'm not sure, but what I could have is I could have something x minus 1, and that was going to be an a. I could have a something x minus 1 squared, and I could have a something x minus 1 to the third, and I erased my squared there. So I'm not really sure which of these I'm going to have. I may not have all of them. I may have x minus 1 and x minus 1 to the third. But if I have repeated linear factors, I have to have one for each power of that repeated linear factor. So again, I'm going to multiply this whole thing right here by x minus 1 to the third. And when I do that, the x minus 1 to the third here and x minus 1 to the third here cancel out. I'm left with x minus 6. And then when I multiply this expression times a over x minus 1, one of the x minus 1's cancel out. So I have a times x minus 1 squared. And then when I have x minus 1 to the third times x minus 1 squared, or over, two of those x minus 1's cancel out, and I'm left with b times x minus 1. And then the last one, x minus 1 to the third and x minus 1 to the third, everything cancels out, so I'm left with just c. So a little bit of simplification here. So I've got 5x minus 6, and then let's see here, when I multiply this out, I've got a times x squared minus 2x, and then plus 1, and this will be, I'll just leave it and do another step, so not d, come on Macaulay, it'll be b times x minus 1, and then c, and then I still have my x minus 5 to the 6th distribute, so I've got a times x squared minus 2ax, and then plus a, and this should be a plus, not a minus. Sorry, I did it twice. How did I do that? All right, that should be a plus. Okay, and then I have bx minus 1 plus bx minus b, and then plus c. So when I'm going to collect and get my quantities together here. So I have a x squared, that's the only x squared term. And then I have, let's see here, negative 2ax, and then plus bx. And then I have, let's see here, plus a minus b plus c. Okay, now check this out. Again, I'm going to have a system of linear equations. Notice on my left-hand side, there is no x squared term. So 0 is going to equal a, because I have 0x squared, so 0 is going to equal to a. My next quantity, I've got my 5, and what I suppose I could do is let's move this down and talk about my b. If I factor out my x from these two expressions here, I would have, do I have a pen? I would have negative 2a plus b times x. Now this expression has to equal 5. So what I'm going to say here is that 5 is equal to negative 2 times a plus b. And then finally, this expression here, this a minus b plus c, it has no x's in it, so it has to equal the constant. So what I can say is that negative 6 has to equal a minus b plus c. So since a equals, I'm just going to work my way down. Since I know what a equals, I can go 5 equals negative 2 times 0 plus b. So b has to equal 5. And then I can come down here and I can plug in what I know. I know that a is 0. I know that b is 5. So negative 6 has to equal 0 minus 5 plus b. Well, or excuse me, sorry, plus c. So what plus negative 5 is c, or is negative 6? Negative 6 has to equal negative 5. Negative 6 has to equal negative 5 minus 1. So c equals negative 1. So I can finish this off. I can take this expression that I had earlier, and because a is equal to 0, I don't even need this term. I can finish it up and say that, let's see here, what do we start with? Okay, 5x minus 6 over the quantity x minus 1 to the third is going to equal 5 over x minus 1 squared minus 1 over x minus 1 to the third. Well, I still kept that one under 30 minutes. I know that one was a long one, and I know that this stuff is not easy. So folks, that is the end. If you have any questions or you think that I made some arithmetic errors and we had a lot of things going on that wasn't the smoothest presentation in the world, please, please, please feel free to email me using the Gmail account that I gave you at the end of school, or leave a comment in the section below. And as we finish up, the Star Wars fun fact of the day: in 2012, George Lucas, the creator of Star Wars, sold his movie studio Lucasfilm Limited. He was the sole and only shareholder to Disney for a reported sum of $4.05 billion. Half of that was Disney stock options. So every Marvel movie, every Disney movie, every Pixar movie, every Star Wars movie that comes out from now on, old George Lucas gets a taste. Would be nice, right? Well, that's all I got. Have a good day and goodbye.